Hello everyone, welcome back to GVM Success Path. In today's video, we are about to understand and prove this theorem. This is an important result in Boolean algebra. We'll break it down step by step from the very basics so you not only memorize the proof but also truly understand the why behind it. If you are preparing for the university exams or just want a strong conceptual clarity in algebra, you are in the right place. So stay with me till the end, and if you're new here, don't forget to subscribe and hit the bell icon for more such detailed explanations. Let's move on. First, let's understand what does these sets mean. Fn of b, Pn of b, which is in the theorem. This Fn of b is the all possible functions that take n elements from b and give one element in b. This is a take and give. Let's see what is Pn of b. Pn of b is the special set inside Fn of b that includes only function made using Boolean expression like and, or, and not. To make it even simple, think of Fn of b as a whole menu and Pn of b is the vegetarian section of it. Neatly defined and structured. I hope you understand what is Fn of b and Pn of b. Now let's read the statement of the theorem. Let B be a Boolean algebra, then the set Pn of b is a Boolean algebra and the subalgebra of Boolean algebra Fn of b of all functions from Bn into b. That means we have to prove, that is to say, Pn of b is a Boolean algebra. We need to prove three things. The first is it is closed under AND operation. The next is closed under OR operation. And it is also closed under NOT operation. Then it contains the constant function 0 and 1. 0 for false and 1 for true. This is what we have to prove. Let's prove each one, that is each step one by one to prove these all. Now let's see the first climb, that is closed under AND operation. Suppose that P of b and Q of b are two functions in Pn of b. That is, we take two functions Pb and Qb in Pn of b. Then we take P of Pb or Qb of a1, a2, an. That means Pb of a1, a2, an and Qb of a1, a2, an, they both are combined under AND operation, that is join. Since both Pb and Qb are Boolean expression, combining them with this join operation still gives us a Boolean expression. So it stays inside Pn of b. So these stays inside Pn of b. Hence it is closed under AND. So now for the second climb, we are using the same idea as the climb 1. So Pb meet Qb of a1 to an is equal to Pb of Q1 to a1 to an and Qb of a1 to an, and both are joined under meet operation. So again, this is a valid Boolean function and remains in Pn of b. So it is closed under OR. Now, of course, for climb 3, that is closed under NOT. We are taking an element PB in Pn of B. The complement of PB of A1 to AN is equal to minus PB of A1 to AN. We are just negating a Boolean expression. The result is still a Boolean expression. So Pn of B is closed under NOT as well. Now for the constant part, we also need 0 and 1. That is a function that always turns false, that always returns false, and another that always returns true to be in Pn of B. These are the simple constant function and clearly a part of Pn of B. So finally, Pn of B is closed under and or and not function and also contains 0 and 1. It satisfies all the conditions of Boolean algebra. So we now conclude that Pn of B is a Boolean subalgebra of Fn of B. So now that's our theorem is proved. So any questions you have about this theorem, just comment below. So now that's it for today's session. I hope you now clearly understand why Pn of B forms a Boolean subalgebra of Fn of B and how we prove it step by step. If this video helped you, and make sure to like, share and comment below with your thoughts or doubts. I'll be happy to help. And if you haven't already subscribed to our channel GVM Success Path, your dedicated space for mastering MSc Maths concept with clarity and confidence. Until next time, keep learning, keep growing. See you in our next video. Thank you.